a little bit early tonight. And the draw lady, or the donation lady. So if you haven't made a donation yet, I mean, this is always free for everybody, but we do appreciate donations. So if you haven't already donated, Laurie will kind of circulate around and gladly take a donation from you if you choose to do so. And if not, you're welcome to the presentation anyways. Okay. So I guess, again, as same as last night, I mean, we're so lucky in Victoria to have this almost limitless pool of really, really good guest speakers. I mean, this being more or less the hotbed of astronomy in Canada, there's just no end of great people to call upon to talk. And Maan Hani talked to us a couple of months ago at one of our monthly meetings, and it was really, really well received. It was a really great presentation. So we've asked him back to talk to us tonight. Unfortunately, the presentation he was going to give us has some technical difficulties on his computer. So, Hitchhiker's Guide to the Galaxy. So, please welcome Maan Hani. So Maan is setting up his computer. He's an astronomy PhD student working with Professor Sarah Ellison at UVic. As a cosmologist, Maan works with cosmological simulations of galaxy mergers to understand the big picture of how galaxies form, evolve, and interact with each other in their environment. So again, this was actually a talk he gave to us a couple of months ago at our monthly meeting. And it was really, really neat. And then speaks with a lot of energy and a lot of enthusiasm, as do a lot of our guest speakers. So once we get connected there, sit back and enjoy.
Awesome. Well, thanks a lot for having me again. I'm very excited to be here talking to you about some galaxy stuff. Unfortunately, my talk that was supposed to be given tonight about black holes is not going to happen. However, we can still chat about black holes later without all the cool movies and pretty pictures. But we can talk about galaxies for now. And I'm very excited to be here, except that as an astronomer I should know it gets cold at night and whatnot, so I'm not really prepared. So bear with me if I'm a bit cold and I may speak a bit fast, but just remind me to slow down. I'm going to give a talk that I gave before to most of you, I guess. So I hope it won't be too boring. I'll try to make it as interesting as possible. So on a daily basis, I'm an astronomer. And what I do is I look at galaxy mergers. So in fancy words, I look at cosmological simulations of galaxies. In fun words, I smush galaxies together in a computer, which is super fun. But about a year ago now, I was visiting my family and I was hanging out with my nephew, and he's about 2 years old, and I was trying to tell him what I do. And I'm hoping to get him to the dark side and doing astronomy as well one day in the future. While describing to him what I do, I really didn't want to use the word researcher because you don't want to scare a kid away. So I decided to just tell him what astronomers actually do. We look up in the sky, we try to figure out puzzles, we try to figure out how things happen and how did we get to be here today. And he looks at me and he says, well, so you're technically a storyteller. Deep down I was happy with that, but at the same time, like the researcher part of me said, not really, I wanna stay as a researcher. So I said, well, I'm a researcher storyteller. So he laughs at me quite a bit, and then after that I ask him why he's laughing, and his answer back to me said, there's nothing called a researcher storyteller or an astronomer storyteller. So, hello everybody, and my name is Maan, and I'm an astronomer storyteller. And tonight I want to tell you a bit about all these galaxies in our universe. So, what galaxies are, they're just big collections of stuff. And almost everything we have in the universe is in the galaxies. So if you were to go outside into space and scoop a tablespoon of stuff, it most likely is in a galaxy. If you look at this image, unfortunately it's not really pretty right now, but all these dots, for the most part, are galaxies, except if you see it crossed around something that's not a galaxy, but otherwise it is. And these funny little things with arms and whatnot are things like our own galaxy. So I've been saying the word galaxy a lot, but I really said it's just collecting stuff, tiny stuff. In fact, galaxies have billions of stars. Just like our sun, there's billions of those. And of course, if we have stars, we have around them planets. So of course, soon there's going to be billions and billions of planets in galaxies. But there's a lot more stuff in the galaxy. There's a lot of gas and dust, just like the dust we kick around in the street every day, and the gas we breathe, and also gas that we see in tubes that light up at night and so on. There's a lot of that gas in the universe, and it all sits in galaxies for the most part. But also there's dark matter. And anytime you hear an astronomer saying dark or black or something of that sort, you should just be very scared. Because that means one thing, and only one thing. We have no idea what we're talking about. So when we say dark matter, it's simply stuff that's there because we see its effect, but we can't really touch it. We have no idea what it really is. We don't really have, in scientific terms, we don't have a good model for it. We don't really know what it is, so we just call it dark matter. It should be matter. We don't really know what it is. Let the term dark and we're good. So for the most part, when we say dark, we don't really know. And of course, there's a lot of that dark matter, but there's better than that. There's dark energy. It's the most amazing term ever. Again, it's some sort of energy. We don't know what it is. It doesn't really behave like we think it does. So it must be dark. So that's how astronomers work. So I showed you a lot of galaxies, but really the nearest galaxy to us that if you look up in the night sky, you could kind of see as a fuzzy blob would be the Andromeda Galaxy. And the Andromeda Galaxy is quite fun to look at. It's absolutely pretty. It has a lot of this dust and gas I was talking about. All these darker lanes, redder lanes that you see are dust and gas. You also see a lot of blue stuff, and that's very, very young stars that are just forming in the last tens of millions of years. And then, of course, you see these little blobs around it that are also tiny, tiny, tiny galaxies that the Andromeda Galaxy has around it. Because every big, awesome galaxy hangs out with little, small galaxies as well. So that's how galaxies really work in our universe. And this is the nearest thing to us. But how long have we really known about galaxies? And what is it that we really think about? So they're not really new. We've seen galaxies for the longest time ever. People in the ancient ages saw this, and without the telescopes in the bottom. And they looked up in the sky, and it was really beautiful, absolutely gorgeous. Looked quite milky, like a nice way in the sky, and they called it the Milky Way. That happens to be our own galaxy. So our own galaxy looks just like the Andromeda Galaxy I already showed, our twin sister. We're a big disk. We're sitting inside the disk, somewhere towards the edge of it, or most of the way up. And when we look straight through it, you see a lot of gas and dust because you're looking through that frisbee, and you don't see much around it. So if you look away from the disk, somewhere around here, you see a lot of darkness and some stars, and likewise on the other side. But the most important part you see is this Milky Way. So we've known about it for a long time. We had no idea what it is, though. We just looked like pretty stuff in the sky. Later on, people started to think of what these things could be, and they decided it is the universe. Up until the 1920s, we really thought we live in an island universe. That's our own Milky Way. And these two guys had a nice chat about it in the 1920s. It's called the Great Debate. And it's called the Great Debate for a reason, because it really is the debate that changed the way astronomy works in the last 100 years or so. So Shapley and Curtis had this argument. One is saying, we live in an island universe. It's our own galaxy. There's nothing else. And all the other little fuzzy features we see that look like galaxies are inside our own galaxy. And then the other guy said, we're not really at the center of the universe. This is an old argument. We've heard it many times. We're not at the center of the universe. These galaxies are their own thing, and there's a lot of galaxies. But it really was left kind of untackled, you know? People were on two groups, no one knew what was going on, and it was alright until this man came along. Edwin Hubble, and he must be important, he has a telescope named after him, you know it's true. Edwin Hubble really solved the issue. Hubble showed up and said, okay, I'm going to measure distances to these galaxies around us. So he measured the distance to Andromeda and other galaxies, and he realized, uh-oh, they're outside of our galaxy. He tried to measure distances to the center of the galaxy, along with other people as well, and they realized, uh-oh, we're not at the center of the galaxy. So we started to drift away from this idea that we're in our own island universe. And we started to think more in the global scale of, oh, we live in a universe that has a lot of these little tiny things called galaxies. And they're not really tiny, but if you look at how many of them there are in the universe, you kind of think they are. So Edwin Hubble really made the big change. But he made another change that is extremely important. He told us that the universe is expanding. And that really changed how people started to think about this business. Because before that, people thought the universe was static. It's just sitting there, you know, hanging out. And then some people thought it should be collapsing or expanding, but they weren't really famous. Because it kind of wasn't really famous idea. But then Edwin Hubble said, uh-oh, it's expanding. And it really changed the face of astronomy. So what really happens? You look up in the sky and you see galaxies. So how does this thing really become what it is today? How do we see galaxies around us? Where did we start from? And of course, I'm going to tell you that something you really know. Things change. They don't stay the same. We all know this. But we have this hard time of explaining it to each other and understanding it deep down. Because deep down we like to think like, it's always been this way. We know it is. But if we think about it, we see things changing in our daily life as well. So if I told you this egg jumped up off the ground, got all together, and jumped into my hand in a video, if you saw that in a video, you may say, you're playing the video backwards. But if you saw it in real life, you'll say, you're really good. But in reality, it really doesn't happen. Things never become less messy than they ever were. So if you break something, it's really okay. It happens. We all break things. So I told you I'm an astronomer storyteller, and I really need a story. I'm standing here saying I'm a storyteller. So my story is, I'm going to try to explain to you how galaxies came to be. And that all started in a painful way, because there's Legos. So this whole thing started with building blocks, tiny, tiny building blocks that started our whole universe. And it didn't start in a pretty manner, because there's Legos. So this is our universe. If we were to break it down to what's in it, you see a lot of these atoms. That's the stuff we know about, stuff we're made out of, or Earth is made out of, stars are made out of, stuff we see in the universe basically that emits light. And then you have all the other stuff. You have a ton of dark matter. I have no idea what it is, but it's a big deal. And then, even worse, we have a whole lot of dark energy. So right about now, you should be raising your eyebrows and be like, so you said you're an astronomer, so what do? You really study this 4% of the universe? And this is what we really kind of do. We study the stuff we can see, and it's a lot of stuff. It's the stuff that's fun to look at. But it's not everything in the universe. Now, a lot of us also study dark matter. They study its effect, and dark energy, but not many of us know what it is. In fact, no one knows. We think we know, but no one knows. So again, back to my story. Our story starts with this. This is the cosmic microwave background. And there's a funny story behind it. Back in the 60s, people in Bell Lab were hanging out and they were trying to come up with a way to have, I guess, a telephone that connects Europe to North America. And that's a great thing. But then they had an issue. You know, they bounced these radio waves, you know, they had these huge scopes kind of thing, pointed at the sky, these dishes, and they were trying to figure out what's going on. But then they decided, maybe there's a better way going than radio, you know, radios don't go that far in distance, so they decided to use these funny microwave kind of style detectors, and they looked like a giant horn basically in the sky. They pointed at the sky and they kept seeing one thing. It's this annoying, pesky noise everywhere. Regardless how they pointed it, where they pointed it, when they pointed it, they saw one thing, this pesky noise. So they didn't know what was going on, and then they decided, we should probably clean our detectors, you know, there could be a problem there. So they went and cleaned the detector. There happened to be a lot of pigeons around and a lot of bird droppings. They cleaned it, they thought, this must solve the problem. So it kind of solved the problem, you know, it decreased the amount of pesky noise, but there still was a ton of annoying noise. And I had no idea what was going on until there was a professor at Yale at the same time. He was friends with some of their friends, and they were working on this idea of a cosmic microwave background. It's basically a light that's hanging out since the beginning of the universe. It's never been touched. So imagine you just point a light at the beginning of the universe and you let it go, and you never touch it again. You never touch these tiny particles of light, and they just stay as the universe ages. At some point, this light that's never been touched will look like this, because no one touched it. It's not going to change. It's going to look the same regardless where you look. So if I point my detectors this way or that way, I should see the same light because no one touched it. And in reality, you do. So it's exaggerated over here because what you see are differences in that light that are 1 in a million, 1 part in a million. And that is an insanely accurate kind of difference. And these, there are new maps of this that are even better and more awesome. But basically what we see here are regions that are kind of tiny bit cooler than others. And then you have regions that are a tiny bit hotter than others. And in astronomy, cooler and hotter means one thing, it means denser and less dense. Just like us, if we really are cold, we can cramp together and we get a bit hotter. If we are hot, we can pull away from each other and we'll just lose some temperature and we'll get a bit cooler. That's the same way gas would work in astronomy. You compress your gas and it gets hotter and so on. So back in the day, about 13 billion years ago, we had this. We had a universe that looked almost the same with tiny fluctuations. Tiny areas were a bit denser, others weren't denser. And the universe worked in mysterious ways. If you have a bit more stuff, you are like the fancy favorite kid in high school. People want to hang out with you. If you have a tiny bit more density, tiny bit more matter, you're up to get more and more matter. So if we start our universe in a very uniform manner, there's nothing different, and give it some time, tiny densities grow and they collect more stuff, and we start seeing them as bigger and bigger structures. And then you can see that places that didn't have really a lot of stuff are becoming more void and empty. And then if we wait a few billion years, just let the universe roll and roll and roll, we end up with something that looks just like that. And if I was to go through and zoom in onto a tiny box like this, if I draw a box like right there and zoom in onto it, I get to see that. And what you're seeing here is a collection of this mysterious dark matter. If you have a brighter object, that means there's more dark matter. Dark matter doesn't emit light, this is just us trying to picture it. And then you have empty areas that really don't have any matter in them. They're just hanging. And somebody may ask, well, okay, great, dark matter, we don't see it. You can really say whatever you want about it and we'll believe you in some sense. You know, we have no idea. So why? Well, the cool thing is that dark matter isn't the only thing in the universe. Remember, we have this awesome 4% we love? This awesome 4% that emits light? That's the 4% we care about here. And the 4% that emits light happens to have this distribution. If you look up in the sky, you will find galaxies. If you were to zoom out very quickly, what you start seeing is more and more and more galaxies. But you don't see them randomly sitting there uniformly. In fact, galaxies cluster together and they form these giant clusters of galaxies and superclusters. Then you have these filaments that contain some gas. Basically, they're tubes that are long enough that connect big densities. So what we believe is that if you have a bigger collection of galaxies, that means you have a bigger collection of dark matter. And there are many reasons we believe that. If you want to talk about it after, I'd love to share with you. So our idea what the galaxy looks like is the following. You start with the galaxy that we can see. You know, it has its stars, its disk, its gas, everything that we like. That's the 4%. There's some of that 4% out here, but it's not a lot. We don't care about it. But then there's this giant, absolutely giant dark matter halo around it. So it's like the same as getting a giant bowl and putting a tiny bit of soup inside it. That's really what's happening in the universe. Every tiny bit of soup, which is a galaxy, has a giant bowl of dark matter around it. And that's its halo. And if we were to track that, it really works magic. It creates the universe again. So what we do these days is we start with our baby universe at time 13 billion years ago, and we let it run with just dark matter in it and some gas. And what we find is we form stars, we have a lot more gas, we start to see dark matter clustering in these nice, lovely filaments and nodes, and we create what we see today. But so far, I've lied to you, and that's not good. Because I told you there's about 74% of dark energy, you know, that energy that we have no idea what it is? Yeah, so that is an interesting thing. I really haven't mentioned it yet. You know, I've talked about the tiny bit of dark matter. Dark energy is mysterious because what dark energy does is it rips things apart. Dark energy makes things stretch really fast. So if we start with a universe, and this picture is absolutely wrong, but for the most part it's alright. If we start with a tiny universe back there, make the universe really tiny, and let it sit there, and then start with the Big Bang, because it all started with it, and let the universe explode outwards. When the universe explodes outwards, what we need to start with is a tiny bit of material, you know, that 4% we all love, it's going to be there. And we're going to start with a ton of dark matter, it's going to be there. But we also need this lovely thing called dark energy. And we're going to also put it in there. And we let the universe expand because it exploded. As the universe explodes out, it starts to cool down. Just like you put a balloon in your car in a hot summer day, it expands. And then if you let the balloon expand even further, it cools down more. And what happens is, as the universe cools down, it gets to a point where this material there's a lot of light to start with, of course. This material does not absorb the light anymore, and it can let it go. And then what we get to see is this, remember this cosmic microwave background thing? We get to see that light, because that's the point where the light doesn't touch anything anymore. It just disperses in the universe. You know? Remember, the key is, this light has not touched anything since a long time ago, about 13 billion years ago. So after that, we let this universe expand even further. The denser things become denser. The less things become void of stuff. And then we end up with our first stars. And really, we have no idea what happened there. But anyway, after these first stars happen, big stars die quickly. They're like rock stars. They party hard, die young. That's how it works. So these big stars die very quickly. And big stars make awesome stuff. It's all the stuff we're made out of. You know, they make these giant elements like iron, uranium, whatever you feel like they make. So after they die, we wait a tiny bit of time and then we start to form these other stars. But keep in mind, we started with dark matter, right? Dark matter is not hot, ever, because you can't heat it. Dark matter just sits there. So as this stuff here is hot and waiting to cool, to form stars and cool even further, dark matter is collapsing and it doesn't really care. And it's making this giant web that we call the cosmic web that we've seen. And this stuff just sits inside. And as time goes, we form more stars and they sit inside this giant web of dark matter and they collapse together. So what we end up with is stars collapsing, making more stuff around them, making tiny baby galaxies. These galaxies get together, make bigger things, and these bigger things get together, they make even bigger things. And we get to today, where we have just beautiful, gorgeous galaxies, like we see around us. So we started with a tiny bit of matter, a lot of dark matter, even more dark energy, we have no idea what that is, and we let the universe expand. And today we have galaxies. Is that good? Awesome.
So what's wrong with that?
Oh, there's nothing wrong with that. That's awesome.
No, you said that the picture.
Oh, the picture. So the universe really did not expand this way. So the universe expanded very quickly. This is area called inflation, and really we need inflation just to make the universe flat and explain a few other things that we don't really know how to explain, other than inflation, of course. And then after that, see this slow expansion here? It's really not that drastic. It's not like the universe expanded and slowed down. It's this expansion happened in a very different way. So as the universe expands, there's matter. Matter does this thing called gravity. Gravity is awesome. It keeps things together, and it keeps the universe together for a while. But after a while, it's like a game of arm wrestling. You know, after a while, matter kind of starts to lose, and dark energy starts to win, and again, dark energy likes to stretch things apart. So see this curve here? Like there's a tiny bit of a curve. It should be more exaggerated than that. And the universe starts to expand very quickly. So I'll tell you more about that later. We're going to talk about our future in a bit. So far I've told you that the universe starts with baby galaxy, starts with matter, makes baby galaxies, and then makes bigger galaxies after that. But I haven't really told you what happens to these galaxies along their way. So don't really panic. We got a way around it. So we start with awesome, beautiful things like this. Remember, there's gas. There's tons of it. All this red, beautiful stuff is gas and dust. And then there's stars. All these dots are stars. And then in the center, there's these supermassive black holes that I was supposed to talk about. We'll talk about them in a bit. And then there's the dark matter we can't see. So for the most part, we have everything we need in a galaxy. Then we can flip this galaxy to the side, and we get to see even more beautiful things. You get to see a disk that looks like a frisbee. You're looking sideways at it. Tons of dust laying all around it. A lot of stars. Not much around it. So when we look at things this way, we really understand how they form. We know how you form things like that. It's quite easy actually. You take a piece of dough and you spin it really fast and suddenly it flattens. We really know how to do that, and that's alright with us. And in fact, this is not everything. There's a lot of stuff that's kind of missing, and I have to mention it because that's my work and I love it a lot. So it's all this stuff around the galaxy, and this is exaggerated again. There's a lot of gas around the galaxy that we don't get to see. So when you look at the galaxy, you see the disk, and the disk is awesome because there's a lot of gas in it, a lot of dust, tons of stars. But the galaxy isn't just sitting there in isolation, like there's stuff around it, and there's a lot of gas around it. In fact, a ton of gas around it. So this is our Milky Way, LMC, SMC, so Large Magellanic Cloud and Small Magellanic Cloud. Then you have this tons of gas, and then it continues outwards, it's not lone. And all this is buried in dark matter. So far I've said a lot of gas. But I really didn't tell you why it's important. I've been using, we have 4% of gas in the universe, it's great, or material. And the reason gas is important, because we made galaxies. I didn't tell you how to kill galaxies. And that's extremely important in today's universe. So we have 4 major ways, or maybe 5, but I'm going to say 4 major ways of killing galaxies in the universe. Not necessarily like killing them in a tragic manner, maybe in a nice, friendly manner. Using the word killing doesn't help, but let's think of it as a friendly way of letting a galaxy just die. And these are our 4 famous ways. We have star formation, we make stars, great. Black holes, interactions between galaxies, and this is really dear to me because I do that. And environment, because the galaxy doesn't live alone. So I'm going to discuss all 4. I'd like to spend more time on black holes just because I promised to talk about them and I'm not. However, if I don't get to spend time on black holes, we can talk about these after we're done. So first we're going to talk about star formation. And star formation is awesome because if you look up in the sky, some of the most beautiful things to see are nebulae. So there are 3 kinds of nebulae, mostly. You have the planetary nebulae, and I'll tell you what those are in a bit. You have supernova remnants, we'll talk about this in a bit. But then there's these awesome nebulae that we may not see a lot, but if you want to find beautiful pictures of astronomy, really galaxies, and those are probably the most beautiful thing. And what you're really looking at here are these pillars, they're called the pillars of creation. Pillars of dust, and they're really, really compact. That's why you don't see anything behind them. So that's again same dust that you kick around the street every day. But that dust is just collapsed together in giant pillars. And these pillars are quite large. In fact, we're talking, for this big pillar, for example, about 100 light years across. So if I want to shine a light here, about 100 years later, it will appear there. So these are huge, huge things. And inside them, you see these tiny red dots. But in fact, these are not really tiny. These are big stars. And they're not red. They're very blue. But we see them red because of dust. And dust does a lot of reddening. So I see there's tons of observers here. I'm sure you guys know all about reddening. But that's the stuff they hate. Observers hate reddening. I'm a theorist. I love reddening because it makes pretty pictures. But overall, that's what you see here. So what really happens is this. You go out in space and you find big collections of dust. And we take one of these cavities here that are very blue and shiny, and we zoom into them, and you see that. So again, we have this dust. The dust sits there, there's gravity. Gravity does the awesome thing of collapsing things. As things start to collapse, they get just hot enough to make this awesome thing called nuclear fusion in the center of the stars. And that is when really stars happen. You get the protostar, which is a big ball of hot stuff, and the moment it starts to burn hydrogen in its core is when it becomes a really full-fledged star. And all these blue things are very young stars. And who has a baby brother, sister, nephew, niece, kids, anything? All of us, kind of? Okay, that's awesome. So babies are super cute. They're awesome. But if you ever try to babysit a baby, really young, we're not talking like 5 years old or so, we're talking like few months old. You don't want to bother them. You don't want to piss them off. They could scream, yell, throw things at you, kick you, all kinds of things. And they could become very, very energetic very quickly. A baby wakes up and in less than 5 minutes they're running around. And I don't know how to do it, but this is how stars work as well. So you have a bunch of gas, it collapses into a star. Of course, not one, maybe many. But the moment you form the stars, these young stars are super, super, super energetic. They're very blue, and they're very energetic. So what they do is they throw these winds outside them, and they push all this gas away, and that's how we get to see them in reality. So they start with a big ball of gas around them, and they push the gas away, and they make these giant cavities that we see around them right here. All that stuff. And that's what baby stars do. But stars don't live forever. Stars die eventually. So we formed a star from a cloud. If we make a small star, like our sun, eventually it will become something called a red giant, maybe 1,000 times brighter than it really is or so. And then it will just puff up, puff up, puff up, and let go. And the moment it lets go, the gas goes away, but it doesn't really just go away. It hits other things. When gas hits other things, it heats up quite a bit. And when gas heats up, it emits light. When gas emits light, we get to see it. So you get to see these awesome, beautiful things called planetary nebulae. They have nothing to do with planets, they're just called so. And then you end up in the center with a tiny little thing called a white dwarf about the size of Earth. However, the fun thing happens when you make a big star. So if you take a star 10 times, 20 times, 30 times the size of our sun, just create it, it's great. It doesn't really live as long, again, rock stars. It grows to become a red supergiant because it becomes very violent very quickly. And right after that, it doesn't just die. Rock stars don't die. Rock stars make a big scene when they're dying. You just see it all over the place. And when these big red supergiants are old, they just collapse very quickly. And if they collapse, they explode. And this is where probably the most violent explosions in the universe happen, ever. Or supernovae. And if you want to look at beautiful things out there, again, supernova remnants, perfect thing to observe. So when you get to see a supernova remnant, you know there was a big star that died one day. But those things are very violent. They don't just die. They die and they make very crazy things. They make neutron stars that you can see as pulsars, or they make black holes. And if you heard of the LIGO observations last year, LIGO worked with probably intermediate mass black holes, a 30 solar mass black hole or so. And we can talk about that in there. But what I'm interested in is this explosion more than anything. When a star dies, it explodes. Explosions are violent. Explosions dump a ton of energy into a system. And if you take a nice sombrero galaxy, beautiful, beautiful galaxy, and you blow up a supernova somewhere in it, it's gonna blow things apart. And the gas starts to flow out. So you can see a bubble pointing out of the galaxy. And what that does, it causes the gas to go up, but then if it's not going fast enough, it comes back down. So it's basically recycling the gas. It makes what we call galactic fountains. But if you have a very powerful supernova, somewhere in the outskirts of the galaxy, you can kick gas outside the galaxy. You can heat up gas. You heat up gas, simply you stop making stars. If you stop making stars, things very quickly become red. And in astronomy we have the saying red and dead. And it's real. Red things are either dead or there's a lot of dust in front of them, but take the dust away, they're dead. So if you have a galaxy and you want to kill it, form a ton of stars very quickly and make them big stars preferably if you can. and then the galaxy dies very soon after that. But stars don't form alone. There's this other thing that we all know and love, it's called black holes. So if we were to zoom in at the center of the galaxy, very much so, what we see is, well, if we can see it, we see a black hole. Around it, there's this disk, tiny, tiny disk, usually thin, not too thick, of very, very, very hot material. So if you point an X-ray telescope at the sky, what you get to see is these guys. And then around it, you have this big donut shape. It's called the torus. So the only reason we care about this is because it affects the black hole. So this torus is a big donut of stuff, material, stars. Sometimes you have gas in it, whatever thing. You throw a star around, it strips it apart, sits in the torus. And then as material sits in the torus and it hits other material, gets hot, loses energy, it settles into this thin, nice, very, very, very hot disk. And this is really what emits the light around the black hole. The black hole does not emit the light. And that material funnels into the black hole. And as it funnels into the black hole, it emits a light because it needs to get rid of its energy. But at some point, the black hole sucks it in. And then when the black hole sucks it in, the black hole grows in mass. And that's how we can grow our black holes. Otherwise, black holes will never grow. But also, sometimes that really doesn't happen. Sometimes the black hole decides to kick that material out. And if it kicks the material out, you get to see something that looks like this. This is an artist's depiction. It's not real. But this is your galaxy. It's called the quasar. So that's very, very high redshift, early in the universe, basically. And very fluffy galaxies because they haven't settled down to a pretty nice galaxy yet. And there's a ton of gas being pushed into that black hole. And as the gas is being pushed in, the black hole doesn't really know what to do with it, maybe, or maybe there's magnetic fields, some kind of crazy phenomenon that pokes the gas out in these crazy jets. And you can see them quite a bit in the radio if you were to look at them. So this is an artist's depiction, but in reality they look like this. So this is a galaxy. And in the center you have a tiny, tiny black hole, about a few million times the mass of the sun. So it's not really tiny, but it's tiny, supermassive black hole. And then this black hole is accreting material, so material is falling onto it, and the black hole is funneling it out. And then it's pushing it all the way out. So what this does, it doesn't only affect the galaxy, but sometimes it can go all the way out, way far from where the galaxy is, and affect everything around the galaxy. And this is an extremely great way of pushing gas out of the galaxy and heating gas up in the galaxy. Because remember, the black hole, look how bright this thing is? That's because of the black hole. There's tons of light coming out of the black hole, bumping into everything around it and heating it up. So you basically just heat up the galaxy. It's too much that the gas can't cool anymore, and the gas can't form stars. And you can't form stars, you become red, and you die as a galaxy. And that's the future of a galaxy. The next important thing, which is super awesome, is interactions. So galaxies don't live alone. Galaxies live with other galaxies. So if I was to take a galaxy like this, sitting there on its own, minding its own business, and being pretty, and let it spin around just because it's a spiral of this galaxy, just like our Milky Way. And if it happens to run around and hit another Milky Way-like galaxies, you can hit the galaxy. And if you can see, there's a ton of gas that's being thrown out as the galaxies pass through each other. So you can see this gas going all the way out there. And then you end up with a funny-looking object that's not really a galaxy. So if I was to play that again, you start with a nice, pretty-looking disk. You let it spin around and go around and around, and then eventually it hits another galaxy. And when it hits it, just look at these tails that throw gas out. They heat gas up, but most importantly, they collapse gas. When gas hits a bunch of other gas, it heats up too, but also shocks, and it can collapse itself. And then it could cause stars to form. And when you look up in the sky, what you really see is stuff like this. So these are two galaxies that hit each other not too long ago. You can see they're still in a very messy, violent merger. And you can see a ton of blue stars, but in here you can see a lot of red stars, and they're really red only because of that dust that makes things red. That's the only reason. In fact, there's a ton of star formation. So if you ask a galactic astronomer and you tell them how do you make stars, many of them tell you just make a merger happen, throw a galaxy on another galaxy and you can cause a lot of stars to be created. And it's an awesome way, but we don't always merge big galaxies together. Sometimes we have small galaxies, like this guy, or like the Large Magellanic Cloud that's coming onto Earth, onto the Milky Way. And this guy will be thrown onto this big galaxy, but what happens is, nothing's gonna happen to this big guy, you know? It's like finding the biggest kid in high school and walking up to them and poking. Like, nothing's gonna happen, except that this guy's gonna disappear and being, we're gonna call it tidal disruption, and it really looks like this. So this is our Milky Way, and these are the Magellanic Clouds, and this is the Magellanic Stream. And what really happens is you throw tiny galaxies at a big galaxy. Just the gravitational pull of that galaxy is so powerful that it rips things apart. Similar to how black holes behave if you were to throw something at them. There's this term called spaghettification. It's real. You throw something at a black hole, but the difference in gravity between the part that's close to the black hole and the part that's far from the black hole is so different that this thing starts to get stretched out and gets stretched out even more. And that is something that happens to galaxies in a less violent manner. So you get these streams because the tidal torques from the galaxies strip things off these small galaxies. But not much is happening to our Milky Way because our Milky Way is so big that nothing happens to it. Yet, these galaxies get deposited onto the galaxy, and then what we get is extra gas. So we're feeding ourselves, which is a great way to grow. And that's how galaxies really grow in our universe. We call it hierarchical formation. And we believe tiny little things, as I said earlier, get together to form bigger things. And last but not least, because I want to keep some time to chat about black holes if you guys want to, is the environment. So again, I said the galaxy doesn't sit on its own. It lives in a busy environment normally, not all the time, but sometimes. And when you have an environment, the environment is really good at doing tons of things to the galaxy. So if you look here, you see two clusters. These are not galaxies, these are clusters of galaxies, 1 and 2, that have passed through each other. They're on their way to get merged. So what you see in the colors are the distributions of gas and dark matter. Okay. So as you see, the gas gets funneled between the galaxies very quickly, rather than the stars or the galaxies. So if you look at the galaxies here, they look normal, most of them. There's nothing fancy happening. But if you look at the gas, it's all over the place. Like, it's really all over the place. So what environments do, they're a crazy good way at stripping gas around and throwing it out. And if you happen to take a galaxy like our Milky Way, put it in a cluster of galaxies, and let it move, you get something like this. I don't know if you can see it, but this is the galaxy moving in this direction, moving upwards, up the screen, and you can see a tail of blue stuff around it. And this is a tail of gas that's being stripped away from a galaxy. And that's what the environment does. If you take the galaxy, throw it through a bunch of stuff, the stars pass through just fine, nothing happens to them. But the gas is easy to mess around with, so you can poke it back. And if you push it back hard enough, you strip it away. And if this galaxy stays in that cluster for a while, which usually does, it really loses all its gas to the cluster. And it ends up being red and dead because it can't make more stars. So my story in a nutshell to you is that we start with a very simple universe. The universe is absolutely very simple. It has a bunch of matter that we all know about, just atoms. They're usually in a plasma kind of sense. And then you have a ton of dark energy, you have some dark matter, and you let the universe expand after the Big Bang. As the universe expands and stretches out, it cools down just enough that a bunch of light disappears, disperses through the universe, and that's what we call our cosmic microwave background. And then, as the matter cools down more, it starts to fall into these big pots of dark matter. We call them halos. So again, big giant bowl of soup, tiny bit of soup inside. And the galaxies start to form. Stars form. The stars get together, form smaller clusters, maybe smaller galaxies like dwarf galaxies. These things get together, form bigger galaxies. And not long after that, maybe half the age of the universe away, we start to see these awesome galaxies out there. Early enough in the universe, they're very violent. They're fluffy because they haven't really settled down into a nice pizza shape yet. They're big, fluffy dough. But give them enough time, and these black holes will go nuts, and then your star formation will go nuts, and eventually everything will settle down into a nice shape. Then you can kill those very easily. You throw them at each other, You get the gas thrown out, you turn black holes on, or you turn on your star formation very efficiently, and the gas leaves the galaxy, and you'll end up with a dead galaxy. But our future of our universe, we're going to keep expanding and expanding and expanding away, that we're most likely going to end up with what we call the giant chill, where galaxies are so far away from each other that everything cools down quite a bit because there's not enough light to keep everything hot. And unfortunately, that's where we're headed, but that's in billions of years, so we don't have to worry about it for now. So thanks a lot for listening.